Okay, so thank you everybody for joining, and apologies about last time. Virgin Media Internet was not great, but you'll be amused to hear that the call dropped early, but I didn't realize that and gave the entire talk. And so it was nice, I had a dry run. Anyway, so the title of the talk is Leveraging Human Data to Bring DeepRL to Robot Manipulation. And the outline is going to be as follows. I'll give a quick introduction to myself and a bit about DeepMind, and then I'm going to focus on two projects which represent sort of the core view that my team has taken and some of our close collaborators on how to attack the manipulation problem in robotics from a reinforcement learning perspective. The first is sort of in the small scale, and the second is about scaling it up. And then, as I said earlier, we'll try to leave some time at the end for Q&A. Okay, so about me, I actually started my career in neuroscience, did a couple of years of research in an fMRI lab, but did a PhD in computer science in the sort of pre-deep learning days on using statistical machine learning to solve problems like what you can see depicted in the right. It is a system that was using essentially online Bayesian inference to help a robot solve an underspecified mobile manipulation problem where it had to reason through unknown physical properties of objects in the environment. And this project was actually a lot of fun, and the final result was picked up by the Discovery Channel in Canada, which is a nice kind of capstone. But to be perfectly honest, the project, by the end of it, I had become a bit disillusioned with the core ideas because, and perhaps this happens when you're too close to your own work, but I knew that there was a mountain of hacks in there and a lot of hard-coded assumptions. You can see the tags on the tables, but there are many other things that would make the system brittle and unlikely to show up in your home anytime soon. And so about the time I was wrapping up, I knew that I wanted to apply machine learning, but at places that were more the squeaky wheel in robotics. I wanted to solve the problem that made it so that we could suddenly start to see robots actually be used in the world outside of auto factories and places like this. And so I joined DeepMind in fall 2015. And we didn't have much of a robotics program then, but it's grown significantly since. And now I currently lead a group called the ARM group, the Autonomous Robot Manipulation Group at DeepMind. So DeepMind, I guess many of you will have heard of, and there might be some sound bites like this. Among these, two in particular caught my eye at that time. One was that just because of the use of deep learning intrinsic to what much of what we do, it can learn automatically from raw inputs. And for reasons I said earlier, that appealed to me a lot. The second is that it was really trying to advance a new notion for organizing science. And that appealed to me because that humanoid robot that I showed you in the previous slide, we built at Georgia Tech when I was there. And it took years to get that thing to be functional. And it was essentially built by undergrads and master's students. And nothing against them, but it takes a long time to build a robot like that when you have a revolving door of students. And so I wanted to be at a place that had an enterprise engineering resource, because I think that's really important for some of the harder robotics challenges that are very engineering intensive. And so within the ARM team, we have this mission, which is to empower anyone to quickly teach a robot how to solve any simple manipulation problem that they can solve themselves. So there's a lot there. I figure there's enough sort of subjective terms in there that regardless of how far I get in my career, I can declare success. But already you can probably tell two things from this. Like one is it's clearly about solving tasks. We want robots to be able to do things, but that's not enough. It's also about being able to communicate those tasks to the robot, which, as I'll argue in the rest of the talk, is a first-class research problem and is very important if you want the robot to do anything outside of a lab or factory setting. Okay. So let me talk first about the general idea of reinforcement learning from demonstrations, and in particular, the last-ditch setting. And this paper was based on IGRA paper from last year. So the project vision here came together in, I guess, late 2017. And the idea was that we wanted to do something in manipulation that a non-academic, somebody that's actually out there practicing robotics in the world, would deem useful. And that was particularly important to me at the time because we'd already seen lots of successes for DeepRL in various simulation domains, and Go, the AlphaGo stuff had already happened in 2016. But I had been hearing sort of increased skepticism among industrial colleagues that these methods were actually useful to the problems that they cared about and that could be applied on real robot hardware. And I had an interesting discussion with somebody, I believe from ABB that year, who described a problem you can see depicted in the bottom of this slide, where they were trying to get a robot to assemble these injection molded parts, these so-called pilot devices that they manufacture. And apparently they had quite good luck with pretty traditional techniques for assembling the entire device, including threading the cap, except for that final flexible plastic clip you see in the bottom that their controllers tended to consistently fail at, because it's sort of a multimodal control problem. You need to know your forces, and you need to know where the prongs are, so that vision has to be part of it. And that was quite difficult to engineer. And we thought that that would be an interesting reinforcement learning target. So that's kind of what started this project. And the philosophy behind it ended up being something that we've stuck with in many regards. And that's that a hybrid approach that allows you to bring to bear a lot of what the classical robotics community has solved, and combine that with reinforcement learning that's targeted to the problems that they can solve is a good solution that probably will stand us well for several years to come. So here's the workflow that we produced in this paper. We wanted to have something that could train from scratch in under a day, and ideally in much less than that, with a couple of hours. So step one is to start by trying to figure out how to define the task for the system. This may be obvious to some of you, especially if you've worked on manipulation before, but our reward function for a robot manipulation problem is very not obvious. It may be true that you could add a sensor to a locomotion platform to give you something that you could use as reward, but in manipulation, the task you want the robot to solve is almost always having to do with the states of objects in the world relative to one another. And in order to hand engineer a reward function, you need to have some high-level features describing those states, like object poses. And doing that kind of defeats the purpose of doing DeepRL in the first place, which is trying to learn the feature representation. And so this really is a first-class problem if you want to solve object manipulation, even in an insertion task, because you don't necessarily know where these plug tips are for the clip you see here. Fortunately, this is actually quite straightforward to solve, at least in this regime, on modern cobots that have cuff interactions with buttons. You can literally just take an in-hand camera on your robot and cuff the robot around your target space and label, like hold down the button for good or bad for whatever you'd like to define your task to be. And we found in this experiment that, at least for this class of insertion tasks, the correlated nature of that data is not a problem. You can perfectly well learn a classifier for it. So the next step is just to train that classifier and also an embedding. And what I mean by that is that just having a reward function that we could use to then go on train an agent end to end would be prohibitive in the time budget we have in mind for this experiment, because a reward signal is kind of a thin bottleneck for information to induce a visual representation. And anyway, we already have one. We've already trained a convolutional net to be able to predict rewards. Why not use those features again for control? And so a chunk of the work in this paper was about trying to add some additional constraints to that classifier so that it would learn features that would be good for control. And this actually has kind of picked up as a theme in the literature. You'll see quite a lot more of this these days. Finally, once you have this reward function, we're going to gather some demonstrations, and not too many, just a few minutes, really, 10, 20 minutes of demonstrations against that reward. And I think you can see on the right a sort of a fancy teleoperation rig where we used one arm to backdrive into another, but you don't need such a thing. We often just use space nav devices in practice. Something kind of like this, which gives you 6-axis control. And finally, once you have your data set, train an agent. And the agent training here has to be, within an hour or two. And actually, the 90 minutes is quite conservative. I think the real robot interaction time is only 20 or 30 minutes, and the rest of it is just sort of inefficiencies computationally in our setup at that time. So for those of you who aren't familiar with off-policy RL, I have a one-slide overview of it. I hope this kind of demystifies the core bit of it. On the right, you'll see the sort of now standard reinforcement learning cartoon. It's an interaction between the agent there depicted by pi and the world, which if you're a robot is depicted by the robot on the right, where at every time step, your policy will receive a state and a reward, and then it has to emit an action that the robot will execute. And those data are fed out as state, action, reward, and next state tuples. And instead of directly being used by the learning machinery, they're aggregated into this persistent storage buffer. We often call it a replay buffer in the RL community, which builds up a database of the experience the agent has seen so far on that task. Once you have that, you can interact with it by sampling mini batches in a standard deep learning fashion to train the network components or whatever other machine learning components you have for this task, for example, an actor and a critic, and then use them to update the parameters for your system. And in off-policy RL, in this paper we use DPG, the important bit is that the actions in this data set don't have to come from the policy that generated the transitions. So I'll highlight that here. So in an off-policy TD update, that action that I have underlined isn't A prime. It isn't the action that the agent actually executed on the trajectory in state S prime. It can be anything. You could use the current policy as you see there, but really that could be anything. Algorithmically, there's nothing that says what the source of that action is. And similarly, you won't see any log policy gradient terms in the policy term. And the nice property about this is that you can replace the agent before it's learned with a human or any other source of action data and train the systems to bootstrap from that. And that's turned out to be a powerful formula. And so this cartoon is sort of the simplest variant you could imagine of RL from demonstration, in which you don't have to make any changes to the algorithm itself. You just put a little bit of effort into doing some first-person teleoperation, let's say, where you can drive a robot through the space nav, put those data in replay, and train as usual. And that actually can work quite well. In this paper, as I said, we were particularly interested in data efficiency. And so we introduced a handful of, I think, fairly small additional tricks that together produced a pretty sizable effect. In terms of the vision and reward model, I alluded to one already. It was this bit about this Gaussian feature regularization, which you could think of like basically training a VAE on the images in the reward data set. We want the latents of that model to have zero mean and identity covariance. What we did technically wasn't a VAE, but morally it's quite similar. We also did basic data augmentations in pixel space, and then added an L2 penalty on the feature distance for when inputs were perturbed. And then finally, on the reward function side, we had multiple, you could think of it like an ensemble, but we only had 2 reward heads that were trained on the latents from this model. And that was really to help prevent false positives during RL, because your agent's trying to optimize that signal, and any pathologies you can find in it. Like, for example, one time we were trying to insert a black clip into a black socket, and it found a black curtain in the background and just held it against the curtain. You want to avoid things like that. And so by training an ensemble and defining the reward function as the and of all of them, you can mitigate that. On the critic side, the first thing we did was use a distributional critic. This is a common technique in the literature now. And as I'll talk about in the second half of the talk, having a distributional critic, like in other words, a value function that outputs a distribution over possible values for a state in action rather than just a point estimate, is a particularly useful tool in the batch setting, or in the pre-training setting, as we do here, where we pre-train on the demonstrations before we run. Also, we don't just have positive demonstrations in the data set. We also have negative demonstrations, things you want the robot not to do. And since we have those in the data set, we also added a classification head to the critic for it to identify every state action pair that it sees as coming from the positive or negative trajectory. And then finally, we regress the episode progress. So let's say that you have a trajectory that was 30 steps long. You can encode the each one of those frames between 0 and 1 is how far it is. It's a bit like a Monte Carlo return if you have a sparse reward function, and force the critic to predict that. And that's value-like information that just helps it quickly snap to a good value function. And then finally, on the policy itself, we had a source of suboptimal or near optimal demonstrations from the human, and so we put an L2 loss to pull the policy towards those actions in the beginning. And that was it. And so you can see the effect of these losses here. Look for the dark colored traces versus the light ones. And it has a particularly sizable effect in the beginning of training. But actually, what I'd like to call out with these plots is a failure mode here, which I've included on our paper on the left, and also another one that we saw that was doing RL from demonstration on the right, and we've seen several times informally since, and across the different algorithms, not just a DPG thing. And this is an open problem when you want to pre-train a RL from demonstration agent and then unleash it on the real world, so it starts interacting with the real environment. oftentimes you have to anneal away that behavior cloning loss, and there's this unfortunate crash that happens in performance as you transition between the pre-training to the online phase. And so far, that is an open problem. Nobody's quite figured out how to solve it, but you can imagine that being quite important for many practical tasks in which it could actually be dangerous to have the performance degrade during the course of training. Here's a picture of the overall model. The main point I'd like to make here is that it doesn't require anything particularly exotic to do RL for a robot manipulation problem. This is on the top, you'll see a quite simple conv-deconv pipeline with a small 8-dimension latent space. There's a couple of reward heads hanging off of it. And then on the bottom, you see that that 8-dimensional embedding goes to the actor and critics, which is the reinforcement learning agent. Okay, so main thing I'd like to highlight here is just the behavior of this algorithm. This, on the right, you'll see demo reel of various sorts of harassments that we subjected the agent to in terms of lighting or moving targets. And in a moment, we'll even bend and twist the plug itself. And the agent was sort of shockingly robust to all of these things, despite only being trained on a subset of it. And this is a nice thing to see that often happens when you run RL on these sorts of tasks with enough data. And I think the regime in which we were operating was a particularly good one for these sorts of tasks. And, especially with the randomization of the socket base, you can see that little white cloth there forced it to reason visually because the socket was randomized. And I think that's a lot of where our robustness came from. And so it's a bit of an older result now. It's almost 2 years back, but I still think this is the best industrial style insertion result that I've seen. Obviously, they're biased. But from RL perspective, these tasks are also fairly simple, and there's no generalization. You have a whole bunch of bespoke work to do for every single task that you want to solve. Of course, owing to the use of DPG, policy RL in general, it can be a bit sensitive to hyperparameters, and really nothing transfers between tasks when you want to train a new system, which is obviously not ideal. And so the main take-homes for this section, I've summarized a few of these already, but the efficiency means you don't need to do sim-to-real or an arm farm necessarily to get RL working on a real robot, but it did require a bit of aggressive pre-training and reusing the visual representation from the reward function. I want to highlight the two in the bottom here. One is that, well, it might sound nice that we can get an agent to go from nothing to solving an unscriptable sort of deformable insertion problem in 4 hours. There's a lot of work that goes into making engineering work that, instead of engineering your solution, instead goes into engineering a safe training rig to make it survive the training process. And that often is bespoke. It was different for the peg insertion task, the clip insertion tasks in a fiddly sort of way. I think that's an open question. And then, of course, as I said earlier, this is still in the small data regime. Okay. So I want to switch gears next to talk about how we scaled this up to a more multitask setting, and something that I think is going to match a workflow with the way that we see the field inevitably going. And to introduce this, I'd like to play a quick clip from a talk that Andrej Karpathy gave at CVPR a few weeks ago, talking about the Tesla autopilot system. And this is very inspirational for us, so I'll play it. It's a Zoom talk, and playing through Zoom's like Zoom section, but hopefully it'll come through. The insert that we play all the time in the team, and this is the bread and butter of what we do, is need to at scale massage and curate this data set so it has all of these cases in it. Otherwise, our network has no chance. So I believe we currently have probably the largest data set of stop signs included by foliage. We have the largest data set of except right turn for a stop sign. And these are all real data, of course. We don't actually utilize simulation all that much. Our bread and butter really is we have 1 million cars out there. They can send us triggers in arbitrary conditions that we specify. And how do you very quickly build out a data set of stop sign precluded by foliage? And that's the kind of problems that we're solving. There's not a lot of sort of like research on that. Yeah, so that bit there was the part that was particularly interesting to us. So you can kind of glean from that talk that they have this big multitask prediction problem. And they have a data set that isn't necessarily labeled for the new tasks that they want the system to be able to perform. And so they have a workflow kind of like what I've tried to depict at the right, where and a system designer will sit down and say, okay, what do we want this system to do? Then they'll engineer a piece of software that will go out and curate for them a data set from their big fleet of cars, particularly for the thing they care about, like stop signs covered by foliage. Then they'll train a model, evaluate it on some subset of the data set, or maybe even on real cars, and then identify new failure modes and iterate. And that's their general workflow. And it's, as you can see, if you followed some of the press on this, has been incredibly powerful for getting their performance to advance quickly. And this is leaps and bounds ahead of anything that we've seen in manipulation. And so the whole premise for this paper was why? Why can't we do this with robot manipulation? What will it take to do that? What are the differences? And so the vision here is really to be able to enable a person to program a robot arm purely by interacting with the data set, as they did in the previous slide. Caveat being that, as with Tesla, you need a seed data set of some sort. In this case, if it's robot manipulation, you need some sort of demonstrations. And so here's the core components of the paper. It's a framework for data-driven robotics, and the core of it is this so-called never-ending storage, which is a persistent data store that's different from the replay memory I talked about earlier. Then we're going to introduce a reward sketching mechanism, which is kind of analogous to the triggers that Andrej Karpathy was talking about. And then finally, we're going to tie these together with a batch reinforcement learning agent, which is the offline learning method that allows you to train up a new task directly against the data without doing system interaction. Okay, so these get combined into a full loop that'll look a little bit like the data engine loop. We'll start with demonstrations. We'll sketch them, and I'll show you what that means in a moment, and train a reward function. We'll use a reward function to train a reinforcement learning agent against the entire corpus, which again is interacting with never-ending storage, and then we'll do evaluation. And the hope is that we can train a novel task with a relatively small number of trips around this circle. So let's start with the never-ending storage in the middle. The idea here is basically to store everything the robot's ever seen. So if you have a robot that has persistent morphology and persistent instrumentation, then in principle, all the observations and actions that the robot's executed should be reusable for a new set of tasks. The task information won't be present necessarily in the data set. That's the open problem that we'll try to address next. But we can gather a huge amount of data in a single database and then solve this downstream problem of how to use that. Like what can we do once we have this large implicitly multitask data set? To start the data set, what we did was built a rig like what you see here. It's a robot with a little basket and some toys in it, and that space nav mouse. And you can walk by after lunch and play with the robot like an arcade game and get it to do sort of whatever you want, whatever's in your head. And you can walk away. You don't have to tell the robot in any way what you had in mind, what it was supposed to do. It just did something that lives in the data set. Okay. Then, separately down the road, when you want to train to do something, you'll do what we call reward sketching, where you sit down in front of a web browser, you open up a page that allows you to search through episodes in the NES, and let's say you want to get the robot to stack green blocks on top of red blocks. You'll hunt down an episode of like a trajectory that you see at the right, and then we have a UI that allows you to literally, with your cursor, scrub through the episode and trace out a reward function for how you think the robot did on that task. And so maybe you'll give it a little bit of reward for grasping the green block, and then the rest of it for the red block. And the reviewers, the raters are told to go above into that green zone whenever the robot's considered successful. It doesn't just have to be tasks that are complete. Here's one. Maybe you found an episode where the robot lifted a green block, but it then didn't do anything else smart. So you can give it some reward for the lifting part, and then just plateau it for the rest until it drops it for that task. Okay. And some of you may be thinking that the ratings here could be a bit arbitrary and very inconsistent across people for sure, and perhaps even across episodes for a particular person. And that's exactly right. So one of the things we found we don't want to do is directly regress these traces for a reward function and try to use that for learning. And so instead what we do is introduce ranking loss using a collection of these hinge loss terms. And this is one of the core parts of the paper, so I'm going to try to explain these carefully. So let's, in these next two slides, the sketch reward is going to be in blue, and the reward model that we're trying to learn is in red. So let's talk about the success term first. as I said previously, success is instructed for the users to be anything in the green zone. And so the first of these two terms is saying, okay, for any of the frames in this particular trajectory, which are above some threshold in green, the tau sub s, we want to make the learned model also be above or not below another threshold, which could be the same or slightly different, in this case, tau R1, as well. And so that's basically a law saying that the model has to pay for anything that's in yellow there. Similarly, any place that the user said isn't in the success zone, which is everything else that isn't gray, has to be below some other margin to tau R sub 2 here, so that in this case, that reward function is going to pay for any of the samples in that red region there. And so between these two, the margin between tau R1 and R2 are quite important. You want to have a margin between success and failure. Having tau R1 be different than tau sub s is arguably less important. I think it was probably just so that the UIs for the person could have a bit larger of a green band because it can be fiddly with the cursor. Now let's talk about the second term. And this ranking term is really what does all the work to convert what we had above, which is just a different way of expressing a binary reward, into a proper shaped reward. And this one operates on an anchor point, which you can see here, xt, with the start, so on each of these traces. And so what that's saying is anytime you have a margin greater than your anchor point, which you can see in blue on your sketch reward. So all those blue frames, all the frames that are highlighted in gray are mu sub s greater in rank than the anchor frame, then that same property should hold for the function you're trying to learn. And so in the bottom, that means that all of the frames that are lower than that margin in that same region should be that much higher than the anchor point on the red curve, on the learning model curve. Okay, and similarly, it can also, that loss will also push down the anchor point. So those two terms combined together give you a span of the range of values from 0 to 1 and a consistent ordering that extracts the ordering information, but not the absolute magnitudes of what the sketch said. Okay, so here's what it looks like in practice. I think this is another example of stacking green on top of red objects. And so the human will come along and sketch a handful of these episodes. Using these sketches together, that's a data set for training a reward model, which we can then apply retroactively to other episodes in the corpus that weren't sketched, but will allow us to basically define an arbitrarily large data set for this particular task. Okay, armed with this reward function, now we can do reinforcement learning. And so that's what happens next. Here you'll see batch RL that trains a reinforcement learning policy. And this paper wasn't about making algorithmic improvements to the batch RL workflow. There's actually been some follow-up work since then. But we actually had kind of an interesting finding here, which is that effectively the same algorithm I described in the first section, you may hear it called D4PG, which is the DPG with the demonstrations, is perfectly capable of learning in the batch setting if you have enough data from enough diverse sources. If you are familiar with this literature, you might expect this to fail because in the off-policy pre-learner can diverge as it bootstraps its own false predictions. But in fact, having data from enough tasks seems to mitigate that effect. And we actually did some ablations where we omitted data from a random policy, which would just kind of wave around in space and periodically close the gripper. And without those data, the agent performs significantly worse. Here's what the model looks like. It's a bit more sophisticated than one in the first section, but again, nothing particularly exotic. You'll see a ResNet backbone here that goes into spatial softmax. The idea with that one, if you're not familiar with it, is to pull each feature map into an argmax in pixel space. And then those features can kind of be interpreted as image position-like features. And the hope is that by having these features there, it's easier to regress object-relevant quantities in your value function and your policy. The one extra bit we added here that you'll see is a bit of noise to the feature maps before the softmax operation, just to try to sharpen their predictions a bit, which seemed to help a bit. And that was, we fed, as you can see here, one of the gripper cameras. I think there were 6 cameras in all for the cell. We fed 4 of them in parallel through this architecture, along with proprioceptive input. Okay, so here I want to show what happens when you apply this workflow to the task I just described for stacking green on red. So one pass through that entire workflow where we've done a bit of demonstration on green and then annotated it, gave us the ability to obtain a policy, to train up a policy like you see here. It can sort of lift it, it's a bit wobbly, and it doesn't do any stacking. But it gave us additional data, and so we can sketch those data. And so if we do that and then repeat the DeepRL process, we see a significantly better agent. Now it was able to pick up the green block, and it seems to have some notion of where the red block is and attempts to drop it on top. So we'll repeat one more time. And in just 3 trips through this process, you can see an agent can reliably kind of pick up and quickly place a green block on top of red. We also compare this to humans. So here what you're seeing on the left was the human demonstration that was used to train it. And then on the right, you'll see the agent execute that same thing at the end of training. And this is the thing we hope to see when using an optimization-based strategy like RL to learn your controller rather than just doing cloning of the behavior, which is that you can exceed the performance of the human demonstration. And then finally, of course, we're interested in how well it generalizes without having any particular training to do so. And so we put some, the green objects, the duck and the dinosaur here, were novel objects that I hadn't seen, and the robot can indeed pick them up. And so you might imagine if you wanted to have a duck stacking agent, you could start with the thing that you've already trained in the block case. The robot will already exhibit intelligent behavior. And so a small number of additional sketches hopefully will get you to the policy that you need to solve that new task. And that's the virtuous cycle that we had in mind for this entire project. Here you see the same behavior applied to a deformable object database. And the main thing to take home from that is just that it illustrates how pose detection and various rigid body assumptions are absent from this framework, and it can work just as well for any robot behavior that you can demonstrate. Okay, so the main take-homes I'd like to leave you with here, foremost, is that the entire concept of the data-driven workflow that Tesla and others have been exploring in other cases is viable for robot manipulation. And while, of course, models are important, the special sauce is the data. And so an argument that I often find myself making is that it's really worth putting the time into building good tooling around your data if you have a data-centric pipeline. And by that, I mean, of course, the sketching interface if you're interested in sketches, but also just having a good UI for exploring the large corpus of data and the never-ending storage or other things like this. And a great deal of our time in this project went into that. In many ways, it was a systems paper, and that's a lot of where the success came from. And then, of course, although I said that we were able to get away with not doing anything algorithmic on the batch RL side, there's clearly room for improvement on algorithms that are more robust to delusions when bootstrapping without being able to do real-world interactions. And so I'd like to wrap up with a comparison between these 2 projects, just to give you a sense of the orders of magnitude involved. On the left, you have the pure RL from demonstration approach. It's single task, and so the reward there is binary, which you can obtain pretty quickly by cuffing a robot around. Similarly, you can quickly cuff a teleoperate a robot around together demonstrations and train a task in a handful of hours. By contrast, in the multitask setting, to get it off the ground at least requires a bunch of sketches on the order of tens of hours. But you don't have to be at home. You don't have to be in front of the robot to do it. You can do it at home or from anywhere you are during this lockdown. Also, the demonstrations, it's a bit longer. However, these tasks, it's a bit apples and oranges. The tasks on the Sketchy project were much more long horizon. And so don't read too much into the difference between those 2. Of course, the data in the sketching case is large and multitask, not even explicitly multitask. It's just implicit. It's whatever's in the data set that you can dream up later at sketching time. And importantly, the embodiment here is persistent. That's the main difference. And so I just want to wrap up with some parting thoughts. I think that it's a good time to start advertising. If you're in this field, the DeepRL can solve robot manipulation problems that are relevant, interesting to the wider community. It's a very different workflow from classical robotics and not always better. There are situations in which you know exactly what your robot to do, and trying to specify it through a sketch or an objective for your learning system is very indirect and doesn't necessarily guarantee that you're going to get the behavior that you want. So it's not always better. But that said, the trend seems to be towards more learning and less scripting, just due to economies of scale. But I'm curious what everybody else thinks is missing. My particular interest these days, I guess, is trending towards vision and 3D vision. I think a lot in the vision community is happening that's starting to be more relevant to robot manipulation problems. Less of an emphasis on classification and more on scene representation and geometry, which I think is really exciting. Okay, that's it. And I would like to wrap up now with the Q&A.